two of them, and then it has three states. One is vertical, and then with horizontal, and then with negative -1. This is a triplet state. And then another possibility is that these two things are aligned, then this is j equal to 1. So there are three possibilities. 1 to m is to the 1, m is to the 0, m is to the -1. Then this is j equal to 0, and m is equal to 0. That's all. I think in the homework, you learn this bound. You learn this bound that m has to be, in the take-home exam, you prove this bound. The total angular momentum bounds the m value. So if j is equal to 0, m is just equal to 0. This is the simplest. You only have one state there. And then this is the single state. I think I remember this as such now. Okay. No, after that you take over. I'm waiting for him to come back, then we can start. Shall we start now? Or? We need to start since he's not back. Okay? So, the thing is that, the key thing is that this expectation value, when predicted by the hidden variable theory, comes out to be slightly different, or quite different from this, that you can actually design an experiment to detect this difference. But then the experiment actually goes in favor of quantum interpretation. It's an amazing thing. So Mr. Bell, wanted to disprove quantum mechanics. He's a big fan of Einstein. But he turns out to be wrong. Okay, so let's look at the hidden variable prediction. So, what happens if we have a hidden variable that A depends on the polarizer position, okay? But there is a random variable hidden inside this experiment that causes the outcome to be plus or minus 1. And if you go and do this experiment, you find that sometimes it's plus 1, sometimes it's minus 1. You never know, okay? So, because sometimes you measure this state and sometimes you measure that state. You never know which state you measure. Quantum interpretation says that the photon is in the linear superposition of two states. And if you put a polarizer pointing in that direction, the photon will sometimes collapse to this state and sometimes collapse to that state. Okay? And that process seems to be completely random. So Einstein came up with this theory. Maybe there's something hidden somewhere. The random variable. It causes this number to be randomly flipping between plus and minus 1. Okay? And then he did the same thing. Of course, the same thing goes for the other polarizer experiment, also driven by hidden variable, lambda. Okay? Then the expectation value of the experimental outcome, which we find to be this thing over here, can be described by all we have learned about probability theory, that it must be the probability distribution function of this hidden variable. We don't even have to define what this probability distribution is at this point, times A lambda, B lambda. So these are all random variables driven by a random variable lambda. Okay? So this must be what hidden variable theory predicts. And then if A equals B, then it's quite clear that if A equals B, then these two will always predict the same value. Okay? Then you always will have these two outcomes to be equal to each other. Okay, so if this guy predicts a vertical polarization, which means that the measurement has collapsed to this quantum state, this guy must also predict a vertical polarization. Okay? So these two would always be the same as each other. If the other guy predicts a horizontal polarization, that means the quantum state has collapsed to this, and then the other one will always come out to be the same. Okay? So then expectation of AA is equal to rho of lambda. If these two are equal, then it becomes A squared A of lambda. This is always a positive number, and it's always a positive number equals 1. Okay, always equals 1. So this just becomes rho of lambda, which is 1. Okay, same as what we predict over here. Okay, always equal to 1 if A is equal to B. So everything seems fine. And if you go through the same argument, let me just use this part of the blackboard and try to keep that part. Okay, maybe I can use this part of the blackboard. Okay. If we use this part of the blackboard, then if A is perpendicular to B, okay, then you can go and argue that this will always be opposite in signs according to the experimental outcome. Okay, always opposite in sign. Then we have this thing. And then if you look at E of AB, this expectation value, there will be always a minus sign difference between A and B. So this would be just minus B lambda, rho of lambda. It's always equal to minus 1. Fine identity, same as what quantum interpretation would have predicted. Okay? The only difference comes when A and B are not aligned. When A and B are not aligned with respect to each other, okay, if A is not equal to B, then you find that the prediction is actually quite different from this. So we have two random outcomes of the experiment, A and B. Sometimes A is positive, sometimes B is negative, and the two do not follow each other now. Okay, A and B are random. Before that, A and B always follow each other in these two cases. In the other case, they always anti-correlate. They either correlate with the same sign or anti-correlate with the negative sign. And somewhere in between, they are between complete correlation and complete anti-correlation. So you expect something like this to happen, that expectation of A and B to be less than 1 because they do not correlate perfectly, okay? Or it should be the magnitude of this to be less than 1. And it turns out that the hidden variable interpretation or prediction will also predict this, but to a different number from what we have from here. Okay, let's go through the hidden variable prediction. And you can easily write down, I will not write the bar now, okay? Let me just subtract two of these numbers and show that let me just write without the lambda, okay? Minus A, B, B prime. And I can write this difference as that, and then I can rewrite this difference to be something that is easier for me to manipulate into a different form, okay? I just add and subtract something to the first term and the second term. So if I add something to the first term, I can write AA, BB, okay? They actually are functions of lambdas too, but I will not write them as functions of lambda. A prime, BB prime, okay? And then rho of lambda be lambda. And then AA, BB, I just subtract something. This is B prime now. Okay, this is prime. Very important. This is prime. Okay, 1 plus or minus A prime, B, and this is B, not B prime. I can rewrite that as that, okay? So if I look at this, what happens is that I have made use of the fact that some of these products are going always to be positive. Okay, so let's see how this is true. Then A prime. I have this term to be exactly the same as this term. Not exactly the same as that term, but A and B prime. B. So if I multiply this term with that term, okay? If I multiply that term with that term, it's exactly the same as this term multiplied by that term. Okay, so I just added the term in and then subtracting it out. So that expression is exactly the same as what I had previously. Then now if I take the amplitude of this expectation value, okay, it must be less than or equal to the, it must be equal to the amplitude of the right hand side, but I will take the amplitude into the argument. Okay, I'm using the fact that amplitude of an integral is less than or equal to integral of the amplitude. I'm going to use this inequality. Okay, amplitude of the integral is less than or equal to integration of its amplitude. So I take the amplitude thing inside, then I can put in this inequality sign, and then I can put my amplitude on the first term, AA, BB, okay? And then take the amplitude of the second term, 1 plus or minus A prime, B prime. Okay, rho lambda, d lambda. Okay, that is what happens to the first term. And then because I take the amplitude, everything, this minus sign goes away. Like A, B prime, this is B prime, okay? Times 1 plus or minus A prime, B. And remember this is B, not B prime. Rho of lambda, d lambda. Okay? So A times B this is always equal to 1. The amplitude of this is always equal to 1 because that's how the outcome of the experiment is. Okay? You either measure 1 or minus 1. And you give the value of A and B either 1 or minus 1. Okay, either they anti-correlate or they correlate in the line case, or in between they should have some kind of correlations, but irrespective of what the angle is between these two polarizers, this is always equal to 1. Is this acceptable? Okay, it's okay, right? So I can set this to 1. I can also set this to 1. Okay? So then I have this thing being equal to just the integral A prime, B prime, rho lambda d lambda, plus the second term I can set this to 1 plus integral 1 plus or minus A prime, B, without a B prime here. Okay, rho lambda d lambda. Okay? So, if I look at this inequality now, EAB minus EAB prime. Okay, if I look at this inequality now, this implies that the right-hand side is less than or equal to, I can add these two terms together, 1 and 1, and this integrates to 1, less than or equal to 2, plus or minus EA prime B prime. Okay, this is just expectation value of A prime and B prime plus or minus E of A prime B. Okay, the right hand side is just equal to that. If I were to assume a hidden variable is at play, somewhere hiding in the background, causing this experiment to be true. So can you get this? This thing must be less than or equal to that thing. I collect the first two terms and make it into a 2, and then this one is just equal to that one is just equal to that. Okay, can you see that? So this is the crucial thing that makes this outcome to be different from the quantum interpretation. So if you look at this, this is something of this form. A positive number is less than 2 plus or minus another positive number. Or not necessarily a positive number, just y. I can call this y. Okay? So this is of the form of the positive number plus or minus a number. I can take this over to the other side, doesn't matter. Is less than or equal to 2. Okay? So this inequality means this. It means that x plus y, which is known to be x plus y by the triangular inequality, okay? But according to this, okay, if y is a positive number, okay, then this number is always not. This number is always less than 2. Okay, this number is always less than 2. If y is a positive number, if y is a negative number, you can always take this negative sign and also convince you that that number is always less than 2. Okay, and so x plus y is. Let me see if this is there a better way to argue this. Okay. So I guess to get this inequality to be in its strictest form, when y is a positive number, you should pick the positive sign. That will make this a larger number. And this inequality has to be satisfied even if y is a positive number. If y is a negative number, then you should pick the minus sign to make this the largest possible and make this inequality satisfied. So if that is satisfied, this is always true. This is always less than 2. Okay, is this clear? Okay. So if you have this now, then what we have is that sum of x and y, assume that x is to be this thing over here, okay? Y is to be that thing over there, okay? If I take the sum of the two, then I will have E AB minus E AB prime plus E A prime B prime plus E A prime B, and the magnitude of this must be less than 2. Okay? This actually has a name. It's called a causal. Actually, it's an inequality that's been refined by these 4 people after Bell has derived this inequality. Okay, this is called the SH inequality. And it's actually something derived after Bell. Bell inequality turns out to be a special case of this. So if we set A prime equals B prime equals C, okay, then what we have over here for this inequality, if we set that to be the case, and actually we can derive Bell's inequality from there, and we will have E A comma B minus E A comma C should be less than 2 plus or minus E C C plus E B C. Okay, I'm just rewriting this inequality on this line by setting A prime equals B prime equals C to be equal to each other. Okay, and ECC is always equal to 1. This is always equal to 1. Okay. And this should be a plus or minus sign here. And then we would try to make this inequality to have its tightest bound, to make the right-hand side the smallest number possible. If we do that, making the inequality to have the tightest bound, we try to pick a way so that the right-hand side is smallest. So we want to pick a minus sign. This is a positive number. We want to pick a minus sign so as to make this number small. And then I have 2 minus 1 and 1. And then if I pick a minus sign, I would have E, B, C on this. Okay. And this is Bell's inequality. Okay. This is Bell's inequality, which is actually a special case of the CH-SH inequality. And if you look at this now, if quantum interpretation would satisfy this, I erase the outcome of the quantum interpretation, unfortunately. But what quantum interpretation says is that E of AB is cosine of 2 theta. Okay, something like that. That's what we found, quantum interpretation. And this is hidden variable interpretation. Okay, if you look at this number and say that if you have a very simple example where the 3 vectors A, B, and C are aligned in this manner, say that this is equal to 22.5 degrees, this is 22.5 degrees, and the whole thing here is 45 degrees. Okay, so if you have this as your example, okay, so the angle between A and B, the angle between A and B is 45 degrees in this case. Okay, so then E of AB is cosine of 2 theta. The angle between A and B is 45, so it's cosine of 90 degrees is equal to 0. E of AC, which is the angle between C, okay, which is cosine of 45 degrees, and this is 1 over root 2. And then E of BC, B and C has 22.5 degrees, so cosine of 2 theta will be 45 degrees, again is 1 over root 2. Okay? And if you plug this into Bell's inequality, on the left-hand side you find that you have 0 over here, and then AC is 1 over root 2. Okay, so on the left-hand side you will have 0 minus 1 over root 2. Okay, less than 1 minus EBC, which is given by 1 over root 2. And this inequality cannot be satisfied. This inequality cannot be satisfied. You see that 1 over root 2, root 2 is what? Root 2 is 1.414, right? 1 over root 2 is 0.707, am I right? Yeah, 1 over root 2 is 0.707. So this is 0.707, less than 1 minus 0.707, and this is about 0.3, right? So this inequality cannot be satisfied. So if you were to do experiment and try to decide who is right, if the experiment comes out to be in favor of hidden variable theory, this inequality will be satisfied. But it turns out the experiment turns out to be in favor of the wrongness of this inequality, which proves Bell's theorem to be wrong. If Bell's theorem is wrong, then quantum interpretation prevails. Okay? So this was done about 1980, about 1982. And after that, then quantum information becomes a very hot field. If you look at most of the quantum computing, quantum cryptography, quantum information papers, they are published in the 1980s period. It becomes a booming field. Okay? So this is what Bell's inequality is, and some people think of this as one of the most important theorems in the last century. Because it's what changes people's opinion about quantum physics and classical physics. Quantum physics is spooky, but it's okay because experiments seem to confirm it. Which means that a particle, a quantum particle, has the ability to behave like a ghost or an angel. It can be simultaneously in different places. Okay? You can actually send information long distance too, like this EPR paradox. Okay, this ghost seems to know about that ghost over there. Okay? And once you find what this state is, the other ghost also seems to know what the other state is. And this is very spooky. Okay. So are there any questions?
So this hidden variable is determined, the value of this hidden variable, according to this formula, it will be determined at the photon source, right? Not
Yeah, it should have been determined before the experimental outcomes.
Okay.
It says that the photon has already collapsed into either one of these two states before the measurement. It's not the Copenhagen School of Interpretation, which is that you do not know what state you are in before the measurement. Hidden variable says that the outcome is either that or that, and it's like your density matrix interpretation. That the thing has already collapsed into one of these two states. Okay, there's no more quantum coherence. So when you perform the measurement, the outcome is entirely determined by a probabilistic outcome, which decides on which state it has collapsed to already, depending on the random variable lambda. There's no mention about what rho should be. Rho can be anything. Rho can be anything, and this inequality should have been satisfied. So we don't even have to mention what rho is, the probabilistic distribution. And then you would arrive at this inequality. Okay? So if there are no questions, I can talk. You want to talk?
Yeah, I can talk about 15 minutes.
Okay. You have more than 15 minutes to talk.
Okay. So you've had about 2 lectures on these quantum computation and quantum information. And actually, largely these experiments, if you think about the experimental work in this field, they're largely done in the field of quantum optics. So we're going to next move on to the quantum optics, and we'll show you how some of these things are actually implemented in experiments. But to start talking about quantum optics, we need to first look at the how do we do quantum mechanics? We first identify some Hamiltonian, right? And then we solve for the eigenstates of the Hamiltonian. We start from here. So the basic quantum optics Hamiltonian is going to start from the Hamiltonian describing a charge coupled to the electromagnetic field. And you see this in your take-home exam, right? Classically, that Hamiltonian will be written by So what this is saying is we have a classical electromagnetic field that's specified by this vector potential, okay? Vector potential. And the scalar potential. Okay? So this is how, this is the classical Hamiltonian of a charge coupled to the electromagnetic field. Let me now tell you that we're going to consider cases where there are no extra charges giving rise to the scalar potential. So this is called choosing a gauge condition. And I'm going to work in a gauge where I can take this to be 0, or and the divergence of the vector potential is 0. So we're only considering radiation fields, no static fields. And this is called the radiation gauge. So under this gauge condition, of course, the Hamiltonian simplifies into just this. of R is some external binding potential that arises from maybe a nucleus or something. So if we're specifically thinking about an atom coupled to the electron in an atom coupled to the radiation field, then this would be the Coulomb potential for the atom. Okay, so maybe Coulomb. Okay, so now I'm going to reduce this to a Hamiltonian that's easier to work with. Okay, and then we're going to turn that into quantum mechanics by replacing P with IH bar, right? Okay. So before we do that, let's think about the length scale. So we're considering a bound charge coupled to the electromagnetic field, and the binding potential arises from the atom. So how much is the electron bind to the atom? Okay. So for the hydrogen, we know that there's something called the Bohr radius, which tells you that the ground state of hydrogen is approximately bound around the nucleus within a distance of a naught. Okay, and this is about 0.5 angstroms. So if I were to draw a heuristic picture of the atom, I would have in the middle a nucleus, and there's some charged cloud, okay, that has a radius of roughly 0.5 angstroms. Okay, and the electron will be located here. Right, this is the ground state. And if we didn't have enough time to talk about the hydrogen atom, but let me just tell you that the ground state has an energy of minus 13.6 electron volts. And the nice thing about the atom is that going to excited states, okay, if I have a principal quantum number called n, okay, which tells you the shell number of the atom, then the energy scales as minus 13.6 divided by n squared electron volt. So the energy scales is 1 over n squared. And let's think about what if it's an excited state that's coupled to the electromagnetic field, what kind of a distance are we talking about? What kind of a size are we talking about for the atom? To do that, I'm going to tell you something from classical physics, which is for the case of this Coulomb interaction, we can use something called the virial theorem, which says that in the case of Coulomb interaction, or this 1 over r potential thing, okay, the kinetic energy T is equal to minus of the total energy, okay, and the potential energy is twice the value of the total energy. Because we're allowing something to be negative, V is equal to, and because we have a bound thing, okay, this is okay. This doesn't violate energy conservation. So in this case, we know that the kinetic energy of the electron around the nucleus is just going to be this binding energy. Okay. So T, which is P squared over 2m, is just 13.6 divided by n squared. Okay. So to figure out how big the atom is, we think semi-classically. Think about the atom as the real classical thing as an electron rotating around the nucleus. What is the kinetic energy? Is the kinetic energy due to rotation? Right? Okay, so I write down the kinetic energy due to rotation, which is omega squared r squared. This is 13.6 electron volts, right? Okay. What is omega? Okay. So roughly speaking, omega is just the so omega is the angular frequency of this rotation. And let me relate this to a omega, which tells you the transition. Okay, h bar omega is equal to delta E from n plus 1 down to the nth state. Let me relate it to this. Okay. So what does this tell you? It tells you how omega scales as n increases. Right? So for large n, which this for large n, which this classical approximation applies. Okay. For large n, we know that we're going to have 1 over n plus 1 squared minus, that should be the other one. So it'll be 1 over n squared minus 1 over n plus 1 squared. This is approximately n cubed, 1 over n cubed. So it tells you that omega scales as 1 over n cubed. Omega scales as 1 over n cubed. Now what about the wavelengths? If the photon is coupled to this, the wavelength lambda scales as n cubed. Right? Yes. So now let's plug this into here. Okay. What does this tell you? It tells you that the r squared. Okay. So r squared is going to scale as n to the 4th. So r is, the radius is going to scale as n squared. Okay. So actually, if you do the rigorous calculation, it turns out that the classical radius, the so-called classical radius, is equal to n squared times the Bohr radius. And it's interesting to think about what kind of n that comes into the experiments in the actual quantum optics experiments. And people actually use n equals to 50. So n squared is like 25,000, 2,500, right? Yeah, so 2,500. 2,500 times 0.5 angstrom, the atom is actually as large as 100 nanometers. The radius of the atom is actually as large as 100 nanometers. Okay. So 100 nanometers atom, if you're coupled to a light with lambda that's equal to 200 nanometers, can you still say that the atom is roughly a dipole? You can't. You'll see the structure of the atom. But the good thing is, we want to couple the atom to a radiation that matches its transition frequency. And I've shown you